Okay, I think we can start. Welcome everyone, and today we are happy to have Maria Nocchi, and she's going to speak about high energy scattering of strings in AdS. So please start.
All right. Well, I'd like to start by thanking the organizers for inviting me and also to the opportunity to share my research. This is some presentation based on work with Fernando Dai and Tobias Hansen. And so this program of AdS Virasoro-Shapiro amplitude started a couple of years ago. And so I'd like to introduce you to this program and then specialize to my research paper about the high energy limit and hopefully argue and convince you that that was the natural step in this program. All right, so some motivation behind that. The central object of study is scattering amplitude. So as you all know, this is the kind of tool that we need to give some prediction for physical observables. And this research area lies at the interface of particle physics, mathematics, and string theory. So one thing is that in flat space, we have some perturbative string theory, which in principle would give us any answer for an interaction process. And you have the nice development of worship methods that allow you to do an expansion. We will review later in a precise way. But unfortunately, this is very hard to extend to curved spacetime in general. So unless you have a very specific background which is well suited to these methods, it's very hard to even extend to the easiest case, which is AdS. And this was the main motivation for our program to start developing some tools to compute string theory amplitudes on curved spacetime. And of course, AdS is the easiest case because the isometries are the same as Minkowski, so that's a good start. So there are two problems. The one problem is very standard, I would say. So if you are studying amplitudes in AdS, in principle, you wouldn't be able to define an amplitude in the standard sense because AdS is a box, so you can't really define asymptotic states. So I would like to show you our way to define the AdS amplitude as an expansion around flat space, and so learn how to analyze and include curvature corrections in a systematic and efficient way. On the other side, maybe more from a mathematical abstract point of view, I'd like to make clear the interplay between string theory and number theory and show how single valuedness was the crucial point that allowed us to solve for the amplitude in an exact way to each order in 1/r, where r is the radius of AdS. All right, so the goal of the program in general is to relate the AdS Virasoro-Shapiro amplitude to a worksheet action. And the goal of my project in particular is to take the further step in this program, which is the high energy limit. So I will try to argue that this was the natural step to take and what we can learn from this limit in particular. So just a very brief review of string amplitude in flat space, because a lot of dictionary and technology will be adapted to curved spacetime very soon. I would say that the main difference between quantum field theory and string theory when we talk about interactions is that in QFT, you do need to insert vertices in your Lagrangian, or if you have non-Lagrangian theories or you like the bootstrap approach, you have to specify the operators in your spectrum and which operators interact, and there are selection rules and all of that. While in string theory, all information about how strings interact, it's already there. So in the sense that you have the standard Polyakov action, which is free, but then you sum over the matrix and you insert by hand, some sense, the vertex operators which describe the initial and final state. So in flat space, you have this nice perturbative expansion that I was mentioning at the beginning. You sum over worksheets of different topologies, and that give you perturbative expansion. So tree level will correspond to a worksheet with the topology of a sphere, one loop to a torus, and so on. So the important thing here is that the sum over worksheets is a sum over Riemann surfaces of increasing genus with insertions of vertex operators. And as a little spoiler, there are some regimes where this sum is exact in the sense that it's dominated by a saddle point. So you can actually do the sum exactly, and that allows you to get some universal result. I will show you when this is the case and why there is a lot of physics there. Yeah, here I just reported some general form, schematic form for the endpoint amplitude, which is a function of the insertions of the vertex operators on these worksheets. And yeah, the two parameters of string theory in this case are the string coupling constant, GS, which is the coupling which you expand in powers of. And then we have alpha prime. I didn't write this explicitly, but it's in Polyakov action. So alpha prime is a measure of the size of the string. And then you can tune this parameter to accept different regimes. In particular, if alpha prime goes to 0, we will see that this is the low energy expansion of the theory, while my project that I will present in the second part of the talk will be the opposite regime, but alpha prime goes to infinity. So it will be the very stringy behavior, but I'll try to explore that. All right, so the takeaway from this very fast review is that in flat space, we can use the worksheet theory to compute string amplitudes. And that's well defined, and we know in principle how to do it in every case. Let's specialize to the case of Virasoro-Shapiro amplitude because this is the object of my analysis. At tree level, I said before that the worksheet has a topology of a sphere. So in general, you would have this kind of integrals where this z is the cross ratios on the worksheet. But for 4-point, you have this very nice and compact form. So just the ratio of gamma functions. And this is the case for each integral which is symmetric in A and B. Actually, it's much more than that. I can refer to like the standard papers by Ivanov and Zerbini in number theory, where they show that these kind of integrals are solvable for any insertions of z and z bar that will require some modification, not symmetric in these gamma functions, but they are all known by now. So for Virasoro-Shapiro, you have these ratios of gamma function, and you can study the various properties. I'll just mention the main points. So first of all, this is crossing symmetric in the Mandelstam variables. They sum to 0. And then there is the TS duality that was one of the very first observations of this model. So for example, if you fix T and you let S vary, you can see the analytic structure of the amplitude. And yeah, so the poles will be at S equal to 4 times n minus 1 over alpha prime. So you get the mass of the tachyon and then all the higher states of the closed string that are exchanged in this amplitude. And that is the key point because you see string amplitudes can be really seen as an infinite number of tree-level QFT diagrams. And that will be either S-channel or T-channel. That depends on whether you fix T and vary S or vice versa, but because of the duality, it is morally the same. Then the next observation is to tune these Mandelstam variables and see what happens in the limits. For example, one very trendy thing nowadays is to study the Regge behavior of the amplitudes that would correspond to take S large and T finite. And now it's well known that if you exchange in general, if you exchange a particle of spin J, that would correspond to an amplitude going as S to the J. And here I just reported very schematically that you have the leading order Regge particles exchange, the states of the closed strings, and that's been studied, and we are still working on how to develop these in curved spacetimes. But for the purpose of the talk, I will focus on the low energy and high energy regimes. For the low energy, I will use that as a tool to introduce single valuedness and see why this is important and natural. And on the other side, the high energy will be the right regime where to do exact computations, at least classically. So let's see how this single valuedness emerge. Again, the central object is a scattering amplitude, because at the end of the day, we want to get some predictions for physical observables. And the best we can do is to provide for some probability for a certain process to happen. And let's do, just for a moment, a step back and go to QFT. In QFT, you have a perturbation theory, which is very well developed. You write an amplitude in terms of a sum over Feynman diagrams. And as I reported here, very standard example, you can have tree-level interactions, and then as you go higher in energy, you have loops and so on. One interesting thing is that at loop level, you get always complicated functions that have branch cuts. Physically, this corresponds to intermediate virtual particles going on shell. And here I would like to study these loop integrals from a purely mathematical and algebraic point of view to see how we usually get tools for Feynman integrals computations and why this is relevant for today's talk, how to extend that to strings amplitudes when we pass from QFT to strings. The first thing that I would like to stress is that as you try to compute these loop integrals, so this is just QFT in flat space, immediately you notice that rational functions are insufficient to write down the answer. You can notice the appearance of the zeta values. So we have zeta 2, for example, and that's the Riemann zeta values at integer values. And then you also have logs, powers of logs, and generalizations, the so-called polylogs. So from the very first analysis of this kind of loop integrals, there are special numbers and functions in loop computations. So the first question that one can ask is whether arbitrarily complicated functions can appear in Feynman integral computations. And without going into the details, I would like to say that Feynman integrals evaluate to a restricted set of numbers and functions that are called periods, examples of which are the zeta values, polylogs, and that's what we need for today. But the key point is that it is not true that arbitrarily complicated functions can appear in Feynman integrals computations, and indeed, just periods can appear. So let's see why this is linked to single valuedness and why this is linked to our project. Before doing that, I'd like to show you briefly the definitions of polylogs because they are the main block of our answers for all the string amplitudes in AdS. And let's start from the classical polylogs that you are familiar with. So we have Lm of Z. They are defined by this series. This converges on the unit disk, but we can continue this to the cut plane by an iterated integral representation, which is the following. And interestingly, you can notice that when you evaluate that at 1, that can be used as a definition of the zeta at m, zeta of m. So let's keep this in mind because the link between polylogs and zeta will be very important in the following. And then we are free to change the kernel of these polylogs and define more general classes of polylogs. One of them I reported here, just as an example. These are the harmonic polylogs. And I'll stop just for a moment to define the dictionary. So polylogs in general are labeled by W, which is a word made by letters x0, x1. So we have an alphabet of letters x0, x1, and of course we have the identity. And we call weight the length of the word. So that's all I will need in the following. And these are defined by this iterated integral representation, and they reduce to the standard powers of log. In the case of the word being just like some power of x0. And these harmonic polylogs are analytic functions of a single complex variable with branch points. So that means that multi-valued functions appear naturally in mathematics in general, as we all know, but in particular, if you want to use polylogs, the first thing to notice is that they are multi-valued. We are free to try to build a single valued image of that. And there are a lot of papers by Francis Brown where he showed that there exists a unique family of solutions that's single valued in the complex plane. And what they were able to do is to build weight preserving linear combinations of the polylog at Z and the polylog at Z bar, such that all the discontinuities cancel, and they are indeed single valued in the ZZ bar plane. Polylogs, again, are examples of periods, so they do appear in Feynman integral computations, and single-valued polylogs are just their images under this single-valued projection. So there is a map, which is unique, which take a multi-valued polylog and returns a single-valued one. As you see, they are exactly the same relations as before, but for example, when you have Z, you have to take now ZZ bar, which is a single-valued combination, and so on. And the last thing that I want to say is that at any given weight, there is a finite dimensional vector space of available functions. That is important because if you want to use these kind of functions for your ansatz, that will be that the ansatz by definition has a finite number of coefficients. So that was for single valuedness from a number theoretical point of view, but where is the physics? And here we reported an example in conformal field theories that at the end of the day are intrinsically related to string theory. The correlation function in CFT is a vacuum expectation value of the product of dynamical composite fields, or if you prefer, vertex operators in string theory. And one of the axioms of CFTs is the requirement of single valuedness of the correlator as a function of the position of the vertex operators in the Euclidean plane. So that means that if you want a physical correlator, that shouldn't have any monodromies, as you vary the position of a given operator around the other one. So that's where the physics centers to explain this requirement of single valuedness. And let's generalize now to string theory. Every closed string tree-level amplitude is a finite linear combination of this kind of integrals. So I showed the case before for the 4-point to get the Virasoro-Shapiro amplitude, but indeed you have these blocks, these basic blocks for any closed string tree-level amplitude you can write down. This is a function of this capital N, which is an integer, and then of these vectors S, N, and then tilde. S is the complex version of the Mandelstam kinematic invariance. So as you see, it contains alpha prime. So the energy is intrinsically related to tuning this alpha prime that I was mentioning at the beginning. And on the other side, you just have some integers that you can choose to reproduce known amplitudes. And for example, the Virasoro-Shapiro in this general setup is just the result for n equals 1 and these values of n and tilde. The next step is to analyze this kind of integrals since they give us the closed string amplitudes for global and local properties. So by global, I mean the properties that you have for any S, and by local, I mean like some specific choice of S. These are both related to the theory of single valued periods. So again, single valuedness appear naturally in the context of string theory amplitudes in the closed sector. And just to give you some intuition behind that, the problem is that in principle, you would expect perturbative gauge and gravity amplitudes in string theory to be very different due to the unequal Warship topology of open and closed strings. But in particular, what you can see is that, as I was saying before, a closed string tree-level amplitude is intrinsically related to a correlator in a CFT because the 2D CFT lives on the worksheet. And in 2D CFT, there is the holomorphic factorization of conformal blocks. From there, it follows naturally that these kinds of integrals can always be factorized into integrals that now are amplitudes of open strings. This is known as KLT relation, and that is just a factorization of closed string integrals into product of a pair of open string integrals.
May I make a comment? So what you're saying is definitely true for standard sort of string backgrounds and which have description in terms of an SR string.
Yeah.
If you have Ramon background, it's actually not much known what to expect. The reason for that is that you can use Ramon vertex operators in an SR formalism, but they are quite unusual. They're non-local effectively on the world sheet. So plus Ramon backgrounds do not have natural NSR description. So they're described in terms of Green-Schwarz strength, which say in light cone gauge is not really a standard conformal field theory with left-right decomposition. So there could be all sorts of subtleties.
Yeah.
You just try to, it's just a not very precise comment, but just a warning that one should be alert to these things in principle.
Yes. Thank you for the comment. That's of course true. Yeah. I was being back here, but this is true. It's not always possible to do this kind of map.
Can I also ask one thing?
Yeah.
Or maybe even two things. You say you insist on single valuedness. So I don't quite understand. Well, to the best of my understanding, if you go beyond tree level, you should have multi-valued amplitudes, right?
Yeah.
So what do you mean by insisting on single valuedness?
So here I was insisting on how single valuedness emerge. So in flat space, you need to go to loop level to get like multi-valued things. So you have these transcendental things, while in string theory, as we were saying, you have the tree level already shows the transcendental functions. But indeed, at tree level, you have single valuedness, but at loop level, that will not be preserved in general. But for curved backgrounds, that was, I mean, surprisingly, that is the case that you can still use this to constrain the entire answer, of course, at tree level. So all of I'm saying is about tree level. But as you go higher in loops, in AdS, for example, you have ways to factorize the loop into tree level things that should be single valued. So we expect that they will be constraining also the loop level answer, even if we analyze just the tree level, as you were saying up to now.
Okay. And what was that? You said that in CFT correlators are also single valued, but I guess it's only true in Euclidean signature, right? In Lorentzian signature.
Yes. Yeah, no,
Yes.
you're right. Yes, I say on the Euclidean plane. That is
Okay. Okay.
yeah.
Okay, thanks.
Yes, thank you. Okay, so this was about the global property of this kind of integrals. On the other side, we can study local properties. For example, if you study the asymptotic expansion, the alpha prime expansion, since alpha prime enters here, you can tune that to 0. That will be this low energy description that we'll provide in a second. And by doing that, you find the asymptotic expansion, and the coefficients of this expansion are multiple integrals of single valued multipolylogs. So again, we have this single valuedness emerging naturally in this kind of computations. And the theory of integration of single valued multipolylogs, which has been developed by Ivanov and Zerbini, show that they belong to the ring of single valued multiple zeta values. Sorry for the bad. It's a tricky name, but I'm just saying that zeta values and polylogs are linked by what we said before at the level of single valued functions and even beyond that. So let's specialize this to Virasoro-Shapiro amplitudes. One of the papers in this program is called Virasoro-Shapiro amplitude and single valued periods, and show why and how these single valuedness emerge. So here just reported the AdS Virasoro-Shapiro, sorry, the flat space Virasoro-Shapiro in a nicer convention, but just to be compact. So now we take this, we take the low energy expansion. Even if I'm not writing alpha prime, this is multiplying every time the Mandelstam variables. And by taking alpha prime to 0, at the beginning I said that alpha prime gives you information on the size of the string. So if you take alpha prime to 0, you're taking the limit of point particle. So you expect to have like the supergravity result, and then you will have an infinite power of stringy corrections. These sigma 2, sigma 3 are just polynomials of the Mandelstam variables that parameterize the result. And these alpha 0, AB are called Wilson coefficients. And the important thing is that only odd zeta values appear in the low energy expansion. And this is very deep because odd zeta are single valued while even zeta are not. And what I mean by that is that if you try to take odd zetas and map them to the single valued one, that will be proportional to the odd one, while the single valued version of the even one is just 0. Of course, I can't go into detail here, but this is well known, and it's deep in the sense that Wilson coefficients live in the ring of single valued multiple zeta values, and this reflects the single valued nature of the integrals that I was showing you before. So this is fundamental for the following. That's the integral presentation on the worksheet of Virasoro-Shapiro, and this Z is just a complex cross relation on the 4-puncture sphere. Now we want to adapt this analysis to curve backgrounds. And before doing that, let's sum up the key takeaways from these review sections. On one side, if you are in flat space, you need to go to loop level to see these transcendental numbers and functions appear. While in string theory, this is different because you have an infinite number of vibration modes in spring spectra, and that introduce transcendental numbers already at tree level in string perturbation theory. On the other side, we review that the low energy expansion of Virasoro-Shapiro amplitude, and actually any closed string amplitude on general level, contains only single valued zetas. So now we want to use what we learned to compute string amplitudes on curved backgrounds where we lack a worksheet technology. And let's see how to do that.
Sorry, can I ask another thing?
Yes.
So on the previous slide, you have the Virasoro-Shapiro amplitude, and you can manifestly see that it's single valued, right, in ST and U. Why do you need to expand it?
Here?
Yeah. Do I understand correctly that you expand it?
So that's just the alpha prime to 0 expansion, right? So you get supergravity, and then as you allow alpha prime to vary, you have the stringy corrections because you're going away from the point particle limit.
Yes, but well, 1 over STU is just, well, a triple pole, right?
Yeah.
And then sigma 2, sigma 3 are polynomials.
Yes, but like alpha 0 AB, it contains like all the single valueness that I was talking about. I didn't report the expression here, but it's written in terms of these odd zeta values, and all the poles comes from there in ST and U.
So these alphas, they are not just numbers.
No, no, no.
So they, wow, so okay, so then I got confused. Okay, thank you.
Thank you. Okay. Okay, so let's present the AdS Virasoro-Shapiro amplitude now. First of all, there is a matter of definition. We will need to define what is an amplitude in AdS, and we do that by using the AdS TFT correspondence. So let us consider the scattering of massless strings. The easiest case is the 4 gravitons on AdS5 process 5, and that is mapped to the correlator of 4 stress tensor multiplets in Mellin space. That's to leading order in inverse powers of the central charge, which is the standard dictionary in the STFT. And if you look at all the papers in the recent literature, it's been shown that if you want to get Virasoro-Shapiro in the structure that we found before, you need to impose the Borel transformation to get the result in flat space. So you take the correlator in Mellin space, you Borel transform it, and you get the first term is Virasoro-Shapiro in flat space, this A0, S, and T, and then you have all the curvature corrections around flat space. So in this sense, I define a AdS amplitude as a curvature expansion around flat space by using this Borel transform. We reviewed the low energy expansion of the flat space Virasoro-Shapiro, but now we want to learn about the higher corrections, these AK of S and T. Of course, each of them admits a low energy expansion, and we have a lot of information on that. On one side, we have to think that we are considering amplitudes in AdS, so that is expanded in Witten diagrams, and we have propagators. And for example, you can take the AdS propagator and expand it around flat space, so you will get the single pole in flat space and then higher order poles. So the structure of poles is well known. In the papers by Fernando and collaborators, they found these dispersive sum rules that constrains the answer. The remaining coefficients are fixed by assuming that they are known these coefficients to be single valued zetas as in flat space. So this single valuedness ansatz is able to constrain in principle for each k the coefficients. In practice, the first two corrections have been computed explicitly, but the algorithm should be able to do it for any order. Modulo, you need some help from integrability for some CFT data. But apart from that, this program would fix all the corrections. Here we are interested more in how the intuition from the worksheet labs in that. And we expect these closed string amplitudes AK, that again are the corrections around flat space, to arise from worksheet integrals similar to the one in flat space. So you take the integrand of Virasoro-Shapiro in flat space and you insert a function of z and z bar. Now we have to choose which function to insert. And the ansatz was the linear combination of single valued functions, such that the low energy expansion still contains only single valued multiple zeta values. And that is super constraining, actually. And the relevant space of single valued functions turn out to be weight 3k single valued multi-polylogs. So this W0 is just taking the factor that you have in flat space. And then as you expand around flat space, you have single valued multi-polylogs that jump at each level by weight 3k, where weight is just the length of the word of the polylog. Again, this is not the result of a direct worksheet computation that is still not available, but it comes from crossing symmetry, the supergravity limit, the structure of the poles, modulo the CFT data that you need from integrability. So we'll start from this.
Can I ask a question? So,
yeah.
So suppose you consider something like AdS3 with a B field, so it's an S background.
Okay.
And then you can look at some scattering amplitude.
Right.
I'm not sure what is known about. Is that statement true in that case? So this is SL2R with the Witten model.
Mm-hmm.
So in principle, 4-point functions are, well, something is known about them.
Yeah, something is known for sure for specific backgrounds. I don't know if this answer would work there. So
yeah, it's a question. So the question is whether this is actually true there. Probably yes.
Probably yes. It's a good question. We haven't checked, so I will not say yes for sure. But I mean, if you have the integrand from the flat space limit of that, you could try to. I mean, you do know the supergravity limit, the poles as well as you were saying. So then it's a matter of finding the right single value polylogs. I'm not sure whether this would jump by 3, because specifically here it jumps by 3 because of the structure of the poles that you have there. But I guess that the DS propagator would have the same expansion regardless of the specific dimension. So I think it is dimension independent. Yeah.
Okay, thank you.
But in the case of AdS3, B field can be added with an arbitrary coefficient, right? So there should be continuous deformation in a sense.
Yeah.
Why? You mean you need conformal invariance, so then it fixes coefficient. Yeah, if you look at conformal invariance, then this is just Witten model, nothing else.
I think this is very constraining. Maybe you do need to do something more about what you were saying, but I don't see any deep technical approaches with that. But yeah, we can discuss about that. I'm happy to try to extend that in any other case. Okay.
Mm-hmm.
Sorry.
Okay.
All right. So the two key takeaways that we can keep with us for the following is that single valuedness plays a fundamental role in the construction of AdS scattering amplitudes out in flat space. And on the other side, as a nice application, we can extract the CFT data from our results that in practice gives us the AdS Virasoro-Shapiro amplitude to any order and compare with integrability results for planar n equals 4 super Young Mills at strong coupling. So up to the second order, you don't need any input from integrability, and so you can do the other way around, and then you can choose what to fix. So either your answer or the integrability results. But apart from this application, now let's motivate why the next step towards the worksheet theory is the investigation of the high energy regime. And to do that, I took inspiration from the very first papers on this subject by Gross and Mende. Well, they are very beautiful papers where they motivated the difficulty to investigate string theory in general, but still the possibility to explore its mathematical structure. And so their aim was to formulate equations and carry out computations that probe string theory in different regimes. So one of the motivation could be, in TFT, the short distance behavior of the theory played a crucial role in literature that gave you the OPE, the RG flow. But what about string theory? So we review the low energy analysis. By taking alpha prime to 0, you get the field theory limit. But the next natural question would be, what about alpha prime to infinity, this very stringy behavior? And I want to argue that this is the right regime in which you can do a connection to a direct worksheet computation, at least classically. Let's review the flat space result, because as for the low energy description, this will be very naturally leading us to the AdS part. The energy limit is defined by taking large S, large T, but you fix S over T. So S over T is kind of the angle of the scattering. The first thing that you can do in this regime, by just staring at the expression of Virasoro-Shapiro in flat space, is to use Stirling's formula for the gamma function. And directly you can write down that in this regime, the amplitude goes like that. So you have a soft exponential behavior, which is drastically different from what happens in PFT, for example. This exponential behavior is universal, meaning that it's independent of the particular string theory and the quantum numbers of the scattered particles. This universality in the original papers was interpreted as some analogous counterpart of the singularities of the OP in the field theory. So they were really trying to get some information on the short on the short distance behavior of the string theory, as I was saying. Let's try to understand this now from the worksheet perspective, because that's at the end of the day what we want to argue here. Again, we have the worksheet integral representation for Virasoro-Shapiro, and that is just 1 over modulus z squared, modulus 1 minus z squared. You take large S, large T with S over T fixed. So you get an exponential from that. That tells you that you can use the saddle point approximation to solve for this integral. And the saddle point is this Z naught, Z equal to Z bar equal to S over S plus T. So we have like the direct way of Stirling's formula and the worksheet interpretation. Before reporting the flat space result, I want to do a little spoilers for AdS to keep a link with my project. For AdS, I reviewed for you the worksheet representation for AdS. So you have Virasoro-Shapiro integrand and the insertion of transcendental functions, the Wn z bar. Even if I'm not going to present the explicit answer because it's complicated, that depends polynomially on S and T. That means that you cannot modify the location of the saddle. So importantly, even if you pass in AdS, to pass to AdS, the location of the saddle is not modified in a 1 over R expansion. So you can still just take the Virasoro-Shapiro amplitude in AdS and evaluate it at the saddle. So what we get is the high energy limit of in flat space and an expansion around flat space of all the transcendental functions evaluated at the saddle point that you find in flat space. To be super precise, what we're doing here is to keep the leading large energy contribution at each order. So we are looking at a regime of large S, which corresponds to the high energy regime, large R, because we always define the DS amplitude as an expansion around flat space, but we also keep S squared over R squared finite to select this leading large energy contribution. Right, so before doing this analysis for AdS, let me just review the result from another point of view, which is the point of view of space-time. We have Polyakov action, the free theory with the insertion of the vertex operators that I talked about at the very beginning. So here I'm using these zeta to call the worksheet coordinates, while z of k, z of I are the punctures. They're taken to be real. You don't lose any physical information by doing that. It's just convenient for our computations. And then we are studying scattering in the massless case. So pi squared is 0, and then there is the usual link between momenta and Mandelstam variables. At high energy, this path integral is dominated by a classical solution that you can write like that. It's in the paper by Gross and Mende. It's actually very nice and easy computation. Then the next step is to plug the classical solution into the path integral, and you get the same high energy result that you would get with Stirling's formula or from the worksheet interpretation. One thing that you can already see is that you have a log of a modulus, so the function is single valued as you move around the position of the punctures, and we want to extend this fact, this intuition, to constrain the amplitude in AdS as well in this regime. The two key takeaways for you: the energy regime, you have either the worksheet representation that gives you the answer in terms of the saddle point approximation. On the other side, you have the space-time point of view in the formalism of path integral that tells you that classical solutions dominate. So what we try to do is to carry this classical analysis for the case of AdS. The first question was how to extend the Lagrangian description, if you want, the path integral description to a space which is curved. And to do that, we introduced embedding coordinates for AdS in the dimensions. So first we had just x mu, with mu being like the coordinate for flat space. Here, this xm as m, which goes from 0 to d, so it's d plus 1 dimensional space. And we select AdS d by taking this constraint. So the contraction of x with itself is minus r squared, and r is the radius of AdS. We input this information by hand through the standard Lagrange multiplier that you can see here. So that this Lagrangian would be just with the proper metric and contraction would be the free Polyakov action, now improved to embedding space. We have the Lagrange multiplier that selects for u AdS. And then we have to input the information of vertex operators because we want to analyze the amplitude for the 4-point amplitude. As you can see from the structure of vertex operators, you can do that by inputting a delta function. And this is your effective Lagrangian for the problem that we want to analyze. Inspired by the work of Gross and Mende, we expect the high energy behavior of the amplitude to be captured by classical solutions, but now in AdS. So let's carry this analysis in all the steps that are required. First of all, by looking at the Lagrangian, you see the Virasoro constraints that are the following for del and del bar. And the equation of motions can be written down. The general formalism is to write them away from the punctures. So that would be the solution by just varying the action. And then you have to impose the boundary conditions. And as a boundary condition, we take this solution. As you approach the puncture, you will get this behavior, which is the flat space result in practice. And these Q, K, M are constants. They can be studied. Everything is in the paper. It's very technical, so I will not report the analysis. But the important thing is that now we have an equation of motion, and we can try to solve it in 1/r expansion and see how single valuedness helps with that.
So you presumably you're just assuming that details like the precise structure of vertex operator,
yeah,
and precise form of the background like Ramon, yeah, it doesn't really matter. That's your kind of implicit assumption, because that's setting which would apply just to bosonic string theory.
Yeah, definitely. That's a very good point. So this is a bosonic model,
yeah,
but all the details, like from vertex operators and prefactors, are subleading in this limit because we are taking large S, large R, but S squared over R squared fixed. And
yeah, the only big assumption is that you assume there's no B field. So this is really, Ramon, well, to make this conformal, you will need Ramon background.
Yeah.
Yeah, that's,
yeah.
Okay.
It is true, but this has been checked. There is a section in the paper, if you want to look, we provide the form of this prefactor that would come from like quantum corrections or the form of vertex operators, but they will not modify the result in this regime.
Okay.
Yes. In this sense, the model is universal, as much more like what Gross and Mende found, the universal result. So yeah, thank you for the question. We want to argue that the result is universal even when you upgrade to AdS-D. And so you don't need all the details of like the quantum state that interact and stuff like that. Since we discussed a lot the flat space scattering problem, we would like to see how the scattering problem emerges as a limit of the DS problem. And the way to do that is to remember that these XM are not free in a sense. So they are related by this constraint. So you use that constraint, you solve for X0. So you plug it back into the Lagrangian, and you have just an expression in terms of X mu. And then you take the flat space limit, which is R to infinity. And in doing that, the X mu are fixed, are constant. And indeed, these X mu are identified with the flat space coordinates. The way that we computed the AdS classical solutions is through an algorithm that constructs the solution to arbitrary order in 1/r expansion. So let us focus also only on the mu indices, because the 0th one is constrained by this embedding space relation. So you have x mu, you expand in powers of 1 over r squared. The first term is the flat space result, and then you have all the corrections. So again, x0 mu is in this form, which is the Gross-Mendel result up to a constant. You plug it so that there is the seed solution. And then what you do is to take this equation of motion and to solve it order by order. I will report to the first order just to show you how single value polylogs emerges, but that's our strategy essentially. So what about higher orders? Our strategy, as I was saying, is to solve equation of motions and Virasoro constraints in this 1 over r expansion. You start from the flat space solution. As we reviewed together, this is single valued as you move around each puncture on the worksheet. So you can write the log of a modulus in terms of a single valued polylog of weight 1. So one letter, which is the puncture of the puncture on the sphere. In the same way, we expect the solution to be written in terms of single valued multiple polylogs, whose letters are now the locations of the punctures. So all of them can appear in principle. And then we want to integrate the question of motion. For example, at the first layer of correction, you have this equation of motion. Of course, you have for x1 that only x0 appear on the right-hand side, and that will be recursively true at each order. And if you plug this solution here, you get this nice form. So on one side, you have the single valued multipolylog with weight 1. On the other side, you have to integrate this del and del bar. And to do that, you need to know how to integrate del bar. That's easy. I would say it's easy for the holomorphic case. You just insert one letter more on the left. This comes from the iterated integral representation that polylogs satisfy. On the other side, the anti-holomorphic integration is more difficult. You don't get just the analogous result, but you also have a sum of terms of uniform weights w plus 1. So this is important to say that holomorphic and anti-holomorphic integration are not on the same level for these kind of functions. But there is a very well understood theory of number theory, and we know how to integrate that essentially. So we brought down a program which solves for you this equation of motions at each level, and it satisfies Virasoro, of course, at each level as well. To give you an idea of how the solution looks like, that's the final solution. So you have linear combinations of single valued multipolylogs of weight n at each order. By pure, I mean that you don't have additional rational functions multiplying that. You just have rational functions in S and T, but that's all the dependence on zeta or zeta I, while the letters of the multi-valued polylogs are the punctures on the sphere. And to sum up, once the seed solution x0 mu is given, which is the flat space solution, the whole tower in 1 over r is fixed by the equation of motion and integration. So you input the knowledge of by Gross-Mendel essentially, and then you have all the tower, and each correction at order n has weight 2n plus 1. And the number of coefficients at each level is finite, and this comes from what I was saying before, that from number theory, you know that it's just a finite vector space of solutions at each weight, which is important. There is a whole analysis of momenta that I will not present here, but I can refer to the paper, and I'm happy to discuss if you want, which is complicated because, of course, as you all know, in AdS, translational invariance is broken, so you don't expect to have momentum conservation and all of that. But still, you want, for example, the flat space momenta to be invariant, and you can also do more by using some deformations of our solutions that are consistent with the equation of motions at Virasoro. But what I care more about here is to present the final result, which I think is important and map back to what we saw in flat space. So that's our final solution. And we have to plug it back into the action and see what happens, because that's what we did in flat space. This is not as easy as I try to show here. So you want to make contact with flat space while still having a finite result. And to do that, you have to add some constants and manipulate the expressions a bit. But at the end of the day, after a lot of work, what you find is that the high energy limit of this AdS Virasoro-Shapiro amplitude is the high energy limit of the flat space counterpart, as we saw before, times this exponential, so in expansion of 1 over r squared. These vi of z0 are combinations of transcendental functions of weight I. And if you remember what I showed you before, the high energy limit that you get just by the saddle point analysis, which is literally take the AdS Virasoro and evaluate that z0 from flat space, you want to have an agreement, of course, and that is true up to this identification. So W3, for example, at Z0 is equal to V3 Z0, but then surprisingly or not, W6 at Z0 is 1/2 V3 Z0 squared. And this is a highly non-trivial test of exponentiation of 40th order. So what we can conclude is that actually curvature corrections in the high energy limit exponentiate, and it is even more than that, the full high energy limit of AdS Virasoro-Shapiro to odd orders in S squared over r squared is determined by the subleading exponent only. So this W3, you can see explicitly that as you expand the exponential again in 1 over r squared, everything else will not be leading in this limit. And that is very nice that you can get the finite R result by exponentiation.
So you claim again that this is universal. So it applied to any, more or less, to any theory with AdS.
Yes.
And dimension is also any.
Yes.
So you're not fixing dimension.
No, we are not. I mean, we are working in a AdS5 process 5 to use the CFT. So we do use like the counterpart from the CFT. But in principle, it should be D independent and specific theory independent, and everything else should be subleading in a prefactor that you can write explicitly if you do need, if you know the background and all that.
So is it true that this formula, let's say, also applies to a single exchange, let's say scalar exchange?
And that's a good question. Let's see. So this is at the level of the total amplitude. So you're taking all the poles into consideration, but I don't want to say yes, but I think it is.
So if I remember correctly, in area space, if you use Mellin amplitudes, then instead of a single pole, you have some sort of a series of poles.
Yeah, because of descendants.
Yeah, so it's not just like you multiply it with exponent.
No, that's right. The position of the pole is modified. But in this regime, I don't know if you would notice that, because what you carry is just the order of the pole. So like in flat space, you have single pole, and then you have jumps by 3 in the order of the pole. Then I don't know how much relevant is that, because you're taking S and T large, and you have S minus something that changes. So I will need to look at that, but I think you could do the same analysis.
Okay, thank you.
Of course. Okay, so I think I will conclude now. I'll try to argue that we are building this problem to give a set of tools to compute string theory, amplitudes, and AdS. This comes from a lot of different setups, and that is actually nice. So we have a DSCFT that allows us to give a definition for what an amplitude is in AdS. We have a number theory with all the tools of integration of single-valued multipolylogs that appear everywhere and specifically in our ansatz. And then importantly, we have the worksheet intuition from flat space, and that was crucial to fix our answer. Again, single valuedness was very important to understand and construct explicitly the scattering amplitudes in AdS, as in flat space. That allowed us to write down the AdS Virasoro-Shapiro amplitude in terms of a worksheet integral. And now a lot can be done in terms of like the various regimes and try to learn about the worksheet action for these amplitudes. I tried also to argue that the next step towards the worship theory for us seemed to be to study the high energy limit, because a lot of physics is there, and especially because of the universality of our result, the same universality, if you want, that that Gross and Mende tried to argue in the original papers. So following the question that I received before, this model is a bosonic model, but still captures the leading behavior at high energy. And our result is universal in the sense that in our regime, which is a specific regime where, again, we keep just the leading large energy contribution, only the first order curvature corrections around flat space are important. And if you wonder how to use all these, because it seems to be a very specific computation, which is nice and exact, but what's more, now you can use this result to constrain the curvature corrections to higher orders. So if you, let me just for a second go back to the expression of Virasoro-Shapiro amplitude as a worksheet integral. So here, as I told you, by now we computed explicitly the first two corrections, and in principle, if you have the data from integrability, you will be able to write down the following ones. And now high energy can be used to constrain the form of that, because they have to match, and the exponentiation is true at finite r. So regardless of the order of the correction, that still has to reproduce our limit. And I think that that's very constraining, that every time that we can add some constraint from an exact limit, that's always very good. And I think with that, I will conclude, and thank you for the attention.
Thank you. Are there any questions?
Again, coming back to this AdS3 case, we can consider, say, AdS3 cross S3 cross T4. Arkady, in my question, I meant that in principle, you can add an SNS flux with an arbitrary coefficient, and only for one particular value of this coefficient, you have a Zumina-Witten model, right? Otherwise, it's a mixed flux theory, and parameter can
Yes, but yes. Yes,
that's what I meant.
You are assuming there is Ramon flux, but I was not assuming. I was assuming no Ramon flux.
Okay, I see.
Just with the middle way.
Well, in this case, if you have mixed flux, well, in principle, probably then this coefficient, arbitrary coefficient, somehow may factorize in front of this invariance W3, W6. Probably it can just be.
But then this argument will not apply, because they are assuming there's no B field in the action. In this argument, it was just bosonic.
We are, yes. So this has to be checked explicitly if the modification is factorizes or not.
I wonder about PSU 2,2/4 symmetry, because in principle, vertex invariant somehow, vertex operator should be invariant with respect to this symmetry if you would like to construct them in a rigorous sense, and should be invariant because this is a global symmetry of the theory. So I wonder if you find in this approach any traces of this symmetry somehow.
No, I don't think so. So somehow the model is blind to.
Should they become covariant? Because
covariant, yes,
yeah.
covariant.
Not
invariant, but covariant. Yes, I agree. Covariant.
But yeah, so the model is blind to corrections of vertex operators. So the prefactor that you would have, we just take the usually to the IPIX, and so yeah, I don't think we see anything about that. But that's a good question first.
As far as I remember, Mikhailov tried to construct vertex operators for AdS5 cross S5.
Yeah.
In Berkowitz, in Q spinner.
Yeah, I think pure spinner would be the kind of people who could match these AdS Virasoro worksheet interpretation with their formalism.
Yeah, but the trouble is in any formalism it's non-Gaussian theory, so you cannot compute much directly. So that's the problem.
Yeah, you need a very specific background that helps you. Otherwise, you have a general setup. I think. Yeah.
Can I? Maybe it's a comment. I'm not sure it's a question. So let's forget about high energy scattering. Yeah. Suppose you start with flat space. You look at Shapiro-Virasoro, and you can reconstruct effective action, which gives you, say, Shapiro-Virasoro scattering of gravitons. and you get an action which is R plus R4 in type 2B theory, etc. So these are alpha prime corrections. So having found this action, you can expand it near some other background, like AdS5S5. If you really know terms with Ramon flux, AdS5S5 is an extremum, so it's a classical solution. You expand near that, and you can then construct the graviton scattering amplitudes on top of, say, AdS5S5. So then my question, so that the point is this effective action is kind of universal. So you can expand, it's a single action which gives you scattering amplitudes on top of different solutions, different backgrounds, just like in ordinary field theory. So the question which I have in mind is if this perspective somehow may be compared to what you're doing. Because formally, I can try to do this large radius expansion also, starting with effective action, trying to scatter gravitons and see.
Yeah, I see. So you're expanding not around flat space, but around.
Yeah, well, you start with AdS5S5, and then you can, on top of that, you can expand near flat space if you can. I'm not sure. Not going through this loop of correlation functions and then Mellin transform, then flat space limit. Maybe there is some kind of more direct way.
Right. Yeah, maybe yes. It's non-trivial though, because even just to get the flat space from AdS, you need to Borel transform because everything is divergent otherwise.
Yeah, because it's essentially a question of boundary conditions. How because you can't consider plane waves in AdS.
That's true, yeah.
To start with, but at the same time, that's what you're trying to do because you're saying we'll expand in inverse radius. So you somehow there is some tension here, which is not clear how to do this directly. Indeed,
I agree. It's very interesting actually, but I don't know if I don't have the right transform to expand. First of all, I don't know how I would generalize in general. So this Borel transform is trivial, right? That you have a transform that gives you the Virasoro-Shapiro in flat space. Because if you just start from Mellin space and you try to resum the alpha prime corrections, you diverges. So.
Yeah, but my point is that I'm trying not to use AdS CFT, so I'm not trying to refer to correlation functions at all.
Okay. So in principle, yes,
the question would be, if you start with AdS5S5 background, how you do this expansion in terms of how you compute scattering of gravitons. And the standard point would be, well, you need to say what are the analogs of plane waves, what you are scattering.
Yeah.
So how you prepare the states. But presumably that should have some expansion in small curvature.
Yeah, I think so, yeah. I think there were some work, I don't remember exactly, but they tried to do that. I think it's very complicated though to give the expansion exactly, and it is true that our program just relies, I mean, it is based on the correlator itself where you have control, but
part of this story is that in fact to do that you will need to know the precise structure of R4 term in type 2B theory, including Ramon flux terms, because you may have terms which have 4 gravitons but multiplied by fluxes, and they will contribute to 4 graviton scattering because flux is just constant on Ramon background. So one needs really to know. What I'm trying to say is that if you start with flat space, you know what's the 4 graviton scattering. But once to apply this to AdS5S5, you really need to know everything at this order, at alpha prime cube order, including terms which involve Ramon background.
Yeah, it's true.
So anyway, this is,
that's very interesting. Thank you. I think maybe the energy is interesting even because that's the regime where you can do the analysis in universal setup. But the general regime, of course, you do need all the details. But yeah, thank you so much. So you're not super expert on string theory, more on the CFT side, but that's what you said expertly.
Any further questions? Okay, since we don't have any other questions, so thank you very much for a nice talk.
Thank you so much for the invitation.
Thank you.